More and more children are out of school, but parents don't want math learning to stop. They're turning to Mathnasium at Home, real-time math instruction tailored to your child's exact educational needs. It's the same face-to-face live instruction used in our centers for over 15 years, now on a computer. Your child can keep their math skills sharp, catch up, or soar ahead, from home or anywhere with an internet connection. To learn if Mathnasium at Home is right for your child, visit mathnasium.com/at-home. Mathnasium at Home, changing lives through math.
Hi everyone, and welcome back to Mathnasium Schoolhouse. Just like yesterday, my name is Sandra, and we are of course here for our part 2 of our Math and Art series. I've been planning this out for days now, super excited. As I mentioned yesterday, I love both math and art, so I'm super thankful for this opportunity to share these lessons with you guys, and I learn from them just as much as you all hopefully do. And so I was just thinking I would love to continue these lessons, combining math and art. So stay tuned in upcoming weeks. I'm sure I'll have a lot more prepared for you because, of course, there are so many connections between these two wonderful subjects. So I think what's best to do right now is to review what we did yesterday and just kind of revisit some of those. I did my homework in completing a lot of the art I guess I should say art projects that we started off together, and honestly I had way too much fun doing it. So I hope all of you felt the same way, and if you didn't have time to do it, you can definitely join me later today and finishing them. I'd love to say hi to some of you. You guys are wonderful in always saying hi to me. A nice shout out to Sarkar, who I know joins us for a lot of these lessons. So super thankful to have you here with us again. Hi Ivan, hi Nimi, hello everyone, hi Shami, and I understand you might be on your parents' account, so if you want to share with me your name as the student, I'm more than happy to see those as well. And I love it when you guys share the grade that you're in. It's very great information for my team and I to really find out who's benefiting from these lessons. So let's go ahead and take a look at what we did yesterday. So yesterday, if you recall, we started off with, and I kind of had fun with this little title card here. So I know it doesn't necessarily, oh, it does fit on the screen nicely. So if you can possibly read my fun little title here, I had fun writing out spiral laterals with, of course, spirals and all of the letters. So we looked at that. So we'll do a quick review of those in just a second, namely the ones that I completed on my own. We looked at, of course, hundreds charts or hundreds grids, and the patterns that we see between numbers when we count on them. So we'll revisit some of that. And of course, number circles. And all of this that we did yesterday was looking at the beauty between math and art, in that when we observe patterns between numbers and we add some visuals to it, art really brings to life a lot of the patterns that we recognize when we do our math mentally in our minds or on our worksheets. It really brings it to life, adds some color and joy to what it is that we're doing. So let's revisit some of those. I'm gonna put that aside, my fun little title card. So this is just a worksheet. I believe it was shared with you. If not, it'll be shared again today. I know it's blurry at the top. There's no need to read that over. I will talk us through that in just a second. But these are two spiral laterals that I created yesterday. And if you joined us yesterday, you'll recall that spiral laterals are formed using line segments of various lengths that we decide whether they're random numbers or numbers generated from a multiplication table, or anything else. And so we'll revisit some of those today. I had also a sequence of just all single-digit numbers, which I formed, and it formed a beautiful spiral lateral, which I'll show you in just a second. But maybe, without maybe showing you the instructions at the top, this is my spiral lateral number 1, and I started off at this dot here. Who can tell me the sequence I use here when I move right, down, left, up, right, down, left, up? What's the sequence used here to form this really cool spiral lateral? Okay. Hi, Deborah. I apologize if I didn't see your name before. Thank you so much for joining us. Okay. What is this sequence here? Let's see if anyone can help me out with that. Let me maybe pull out my marker here. So as we said yesterday, if you did join us, if not, that's okay. A spirolateral is formed with line segments of various lengths. In my case, I went right by 1. So that is the first part of my sequence here, so I'll write it down there. Then I went down by 2. Then I went left by 3, perfect. I see a comment come through. And then up by 4, and then you can hopefully start to see that it just continued. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And one of the questions I left you with yesterday was to think about, when do my spirolaterals meet back at the starting point, and when will they continue forever, never getting back to that starting point? And you can see this is one of those cases where if I continued this, if I had a bigger grid, a bigger space to continue it, it would just continue going up into that corner. Exactly, you guys are recognizing the pattern there, right? It'll never get back. Why? Because I have, maybe one reason could be that I had 4 steps here, and every time I'm going down by 1, I'm going right by 1, down by 2, left by 3, up by 4. Okay, so there's no opportunity to kind of mix and match the directions with these lengths to hopefully come back. And we'll see how that maybe changes in some of our other ones. And so I kind of left you, that one was exercise 1, and I kind of switched it up just a little bit in exercise 2, where I kept the same numbers, just the reversed order. So I asked you to draw a spirolateral with the sequence of 4, 3, 2, 1. So this one here is 4, 3, 2, 1. How do I know that? Well, again, I'm following the same directions. Right, down, left, up, right, down, left, up, right, down, left, up. Those are just my directions. You could have decided to go left, up, right, down, if you wanted that kind of spirolateral. And you can see I went 4, 3, 2, 1, 4, 3, 2, 1, 4, 3, 2, 1. Really fun to make them. You'll see in my next image I made a mistake once, so you have to just keep in mind the number that you're on. All right? Yeah, and so great question there. What if you did 1, 2, 3, 4, and then 2, 3, 4, 5, then 3, 4, 5, 6? That's the beauty of these, right? You can switch it up and then compare. And I believe that's one of the questions I left you with to investigate for yourself is, well, what happens if I compare this one with, let's take one that William offered for us, 3, 4, 5, 6. How would that change, right? And so you'll still notice in the ones that you suggested, William, you still have 4 numbers in there. And so my prediction, which as a mathematician I'd want to prove for myself, is that it'll never get back to that starting point, okay? And Deborah, very great observation. It does look like a spring, or, which is why we call it a spirolateral, it looks like a spiral, just made out of lines, not curves, right? So those were the first 2. Then I kind of extended it a bit further, of course, to have some more fun. And I asked you to draw a spirolateral. You can see my little mistake up here. Oops. Using the sequence 1, 2, 3, 4, 5, 6, 7, 8, 9. So I had a lot of steps involved in that. So maybe I'll help you follow along here. So here was my starting point. Same directions as before. Right, down, left, up. Right, down, left, up. But I was following a longer sequence of numbers. So I went 1, 2, 3, 4, 5, 6, 7, 8, 9. And then when I got to the end of my 9, I had to start all over, right? Because we're repeating it. And you can see in this case, when I repeated it 4 times, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, I got back to where I started. I love that. It's not a mistake, Sandra. It's a happy little line segment. I totally agree. It was too excited and wanted to grow, grow, grow. Which is why I kept it, right? I could have printed a new page, but I decided, you know what? That's what math is all about, learning from mistakes, right? Or happy little line segments. And to me, I don't know about you, I love flowers, so I try to recognize them everywhere. I kind of like this idea that it's some abstract form of a flower, right? I think it's a beautiful one formed from just, again, using a sequence of numbers 1 through 9. So I hope that maybe you try this out on your own too. And hopefully you'll know you're right when you end up back where you started. So I was crossing my fingers the whole time that I didn't make any errors in my measurements. Right? So I left you with some questions to consider here. Some of them I've already reviewed with you right now. When do you think you'll get back to your start? When do you think you never will? And consider this. We have one more spirolateral to look at. But one of the investigations and explorations I'd love for you to take on, maybe when you do this with a friend or family member at home, is what if we don't always turn by 90 degrees, right? We don't simply go right, down, left, up. What if we go, and I'm going to ruin my image here just the slightest bit, what if we decide to turn by 45-degree angles? So something like that. How does that kind of change this image? How would that possibly change this one here? And one prediction you might make, one guess might be, well, it kind of looks like it'll take on the same image, just maybe rotate it a bit, maybe by that 45 degrees. So if you want to take on that challenge and try it out, go right ahead. And it kind of looks funky just from my artist side, using a different color and drawing, I did mess up the measurements here on purpose, but kind of drawing it over top your previous one. I agree, Deborah, it'll look really pretty, right? If I had a black one over this, maybe if I did another rotation, could be some really cool art form right there, right? Something worthy of hanging on your walls. So there's that, and let's look at my other spirolateral that I formed, this one here. How about I let you guys take a look at this one here. The starting point, which might be hard to see, is right over here. Maybe you can tell me what sequence of numbers this spirolateral was formed from. And maybe you can just tell me the first few numbers if you don't want to count all the way. But go ahead and try to find out what sequence of numbers I used. I'll wait till I see maybe one or two numbers pop up. So again, I go right, down, left, up in all of my spirolaterals. Okay? So that's something that is useful to know if you're looking at someone else's spirolateral. Which directions did they use? 2, 4, 6, 8 are the first few numbers. Very good. Yes, that's exactly right. 2 right, 4 down. Yeah. 6 left, 8 up. Then it looks like I don't continue that just yet. I still have 1, 3, 5, 7, 9, and then it starts to repeat itself. And again, it looks like it was repeated 4 times. If you notice, we'll look at some symmetry later on today in our lesson, but there's some sort of symmetry going on there, which we'll talk about soon. But your guys are offering the right answers, 2, 4, 6, 8, even numbers. It does go beyond that to odd numbers as well. And what we talked about yesterday is spirolaterals really help us visualize also our multiplication tables. So if you joined us yesterday, and if not, that's all right. I'm going to put this to the side for just a second. We looked at the 2 times tables, which is exactly what is formed here. Right? 2 times 1, 2 times 2, 3, 4, 5, 6, 7, 8. Can I squeeze in 9? Yeah. Okay. And what we talked about yesterday, thank you for sharing, yes, Sirkar and Shamit, was that when you have double-digit numbers, the way that you're going to use that in your spirolateral is to add up each value of the digit. So in this case, in our sequence, we'll have 1 here, which is where that 1 is showing up in my spirolateral. Here you'd have a 3, which is where I go down by 3, a 5, which is where I went left by 5, 7 up, and finally right by 9, because 1 plus 8 is 9. And then if you think about the next multiplication fact, which is 2 times 10, you get 20. 2 plus 0 is 2, and we talked about this yesterday. You start to repeat the numbers in your sequence. And so these are all the numbers that you'd use, which is what I used here in my spirolateral. Okay, I stuck with 2s, but if you're super comfortable with this, extend it to 3s, 4s, 5s, revisit the lessons we had with our multiplication series. And once you know those facts, visualize them for yourself as kind of a reward, a piece of art afterwards. So those were the spirolaterals. I hope you really enjoy that. I think they're gorgeous. Imagine this colored in. Oh my goodness, it would look so beautiful. And then we also talked about hundreds grids, right? We looked at hundreds charts. I pulled out what we call a desk tool at Mathnasium, and we looked at some patterns. So I kind of did my homework here on another hundreds chart. Yeah, perfect. Oh, I'm seeing you guys talk about your art classes, and when you do paper art, we use this. Very good. I love to hear that a teacher incorporates math in a lot more areas than just the math class. So what I did here is I took my red pen, which is why it might be difficult for you to see, so I'll use my red marker here, and I highlighted all the multiples of 2 in red. So you'll see that here. And go ahead and share with me, what pattern do you observe for the multiples of 2? So I have them all here. Visually, what pattern do they form in this chart? So I helped you out by just really emphasizing that red in this image here. They're forming what types of lines? Not horizontal, but vertical, right? It almost looks like vertical strips on this hundreds chart that I have here, right? All the multiples of 2 found in this column, then they're also found in this column. Skip one, another column, skip one, another column, and so on. And you guys helped me out yesterday in telling me, hey Sandra, those are also the even numbers, which is exactly right. Then I took my green, which is also a bit too difficult to see here, so I'll help you out. And I looked at the multiples of 4. I wanted to see for myself, I was curious as a mathematician and an artist, if there's some visual pattern that's observed. So I'm going to highlight them, and you guys tell me if you see some pattern. Keep on going until maybe I see someone offer an answer. I'm going to cheat a little bit and go down this column here, because I've identified a pattern. How did I know, without even counting by 4s, without trying to recall all my 4 times tables facts, that I could circle all of those and confidently say that they are multiples of 4? Well, I recognized a pattern here that after I filled in the first few, because I knew those really well in my mind, I knew my 4s times tables up until a certain amount. Yeah, it is hard to see with all that color, I know. So let's just focus on that green. So I saw the 4 and the 8, then the 12 and the 16. Then in the next row, I had 20, 24, 28. So you could start to see in each column, I'm skipping a row for the number, right? And because all the multiples of 4 will still be even numbers, great, I'm seeing it. I'm seeing a comment offered, yes. Then they'll still be in the same columns as the multiples of 2, but just not every number, so I'm skipping them. Pretty cool observation, right? They go down but skip 1 square, great description. Then in blue, I took out my blue marker and I highlighted all the multiples of 9. And you can see a really cool pattern that formed here, which is they were all on the diagonal. Okay, so if you want to think about why after today, that would be a really cool observation to make. And consider the fact that 9 is 10 minus 1. So think about that one. And then I looked at the opposite, which was 10 plus 1, which was 11, and I saw that it lies on the other diagonal. So these are all the multiples of 11 in black. So spend some time maybe later today thinking, why does that happen in this hundreds chart? And I kind of offered you the hint there, right? If 9 is 10 minus 1, we're not going all the way to the next row and right below it. We're going one less than it. Okay? And same goes, just maybe the reverse for 11s. It's just 1 more than 10. So there's that. Really cool patterns we can also make in a hundreds chart or a numbers grid, whichever you want to call it. And same goes for a numbers circle. And so we talked about maybe connecting dots, connecting numbers that are multiples. And so I kind of started one off here. And this is just a visual representation of a number circle. But what is really cool, if you want to take this a step further, is taking string and actually attaching to these numbers here. So try that as a math and art project. That would look super gorgeous. And it kind of reminds me of a dream catcher if you've ever seen one of those. Okay. So I'll show you what I did here. I took out my red, for example, and I connected every fourth dot. So I looked at the multiples of 4 again. So 0 to 4, 0 to 8, 0 to 12, 0 to 16, 0 to 20, and so on. And it formed a pattern. And then I took out my green and I looked at other multiples. And I didn't finish it. It would have taken too long. And again, I don't want it to be too confusing on this number circle. But there was that. But then I did a cooler one. I'm going to show you this one here. Look at this one. I'll explain to you how I did this in just a second. And it's, again, in the package that will be shared with you. I've left you with the instructions. What's so cool about this one? I'll let you look at it for a bit. And then I'll highlight something here. It looks like you're looking up at a bridge. I love that explanation. So going back to this image here, yeah, that's a wonderful way to look at it. Very cool. Yeah, the perspective, very nice. Very creative. What about here? What do you think is formed here? What does it look like? It also looks like you're above a circus roof area. Very good. Okay, so what does this one look like here? Oh, I can see the connection is a little bit slow, so I'll hold off. It is in the shape of a heart. That's right. It kind of looks like this. So this is actually called, in math, this shape is called a, spell it out for you, a cardioid. Okay? And the cool thing about this one is it was formed from just straight lines. Look at that. So all I did here is I took out my straight edge and I connected all the doubles together. And again, we started this off yesterday, if you can recall that. So we looked at, I have red numbers going all around and then green numbers. And I connected all the doubles together. And when I did that, it looks like I drew a curve here, but really this is all formed from a bunch of lines intersecting each other. And the same goes on this side because it's symmetric, right? If you can recall symmetry, if I were to fold this circle right on this middle line, I get the same shape on both sides. And it does look like a heart. It's the math heart. This is my favorite one. Okay? And what you can do on your own after you formed this is really take this a step further and create a bunch of curves with a bunch of lines. So what I did after that was I just created for myself a set of axes, and I decided I'm going to connect the 1 with the 1, the 2 with the 2, the 3 with the 3, and so on. And it almost looks like, with all these lines, it formed a curve. But I didn't even take out my marker and create a curve. It was just made from a bunch of lines intersecting each other. And this one here, the shape that's going to be formed here, if I extend it, is called, in math, a parabolic curve. Okay? So another word that you'll see later on in your math studies is the word parabola. So two really cool shapes we can form and use in some of our art pieces just from a bunch of lines. How cool is that? All right. And you can take that a step further, if you'd like, and create art pieces where each piece has a bunch of lines that intersect to create the curves. Okay? So let's remove this. And now let's look at two theorems that we didn't get to discuss yesterday. So yesterday, what we ended off with, so I'm pulling up this, it looks like I'm in the net. Yes, very good. I love your observations. These are really nice. So yesterday we were able to form a 7-pointed star. And the way that we did that was we had 7 dots all along what would have been a circle. So I kind of traced it on top of a circle. And we formed this star by connecting every 3rd dot. So if you're interested, or sorry, every 4th dot. Okay, so if you're interested in building that, you can go ahead and check out yesterday's lesson. And one challenge that I left you with in the package was to take out some colors and color in your star such that, and this is the catch, any space that is beside each other cannot have the same color, right? So for example, I decided to color this shape that's formed here purple, which means I couldn't have a purple here, and I decided to just take out my yellow. But what does that mean? If I'm trying to use the least amount of colors, I can color in all of these outside shapes purple. Not the best coloring, but it's really fast coloring. Okay, let me just turn this around. Which means, using that same idea as I explained before, this wasn't the most symmetric star that I could create, but there would have been the same triangle formed there, and all of them would be yellow. And so the middle shape couldn't be yellow, but it could be, if I'm trying to use the least amount of colors, purple. Because this purple is not touching any of the other purples. So how many colors did I have to use here to color in this shape? Only 2. Okay, so let's keep that in mind here. So 2 colors. There's a very interesting math theorem that comes out of this, which is called the 4-color theorem. Any guesses what the 4-color theorem tells you? What would it mean? So mathematicians have found, okay, good, 2 colors. Mathematicians have found that the 4-color theorem means that you're able to color in any drawing like this, such that no 2 spaces share the same color if they're touching each other, if they share an edge. And it's impossible to use more than 4 colors. That all you'll need is at max 4 colors. Okay? So I challenge you, for example, to help me with this image. So I'm going to draw one on my whiteboard. Let me just pull that off to the side. So I'm going to do my best to draw circles here. So let's say I have a big circle, not too bad. And then I have a smaller circle, and then a really small circle. And then let's cut up in here, and then cut up in here. Okay, how many colors do you think I would need for this one? Before you maybe guess, think about it for a second. How could I possibly color this in so that no 2 spaces that are touching each other have the same color? So let's try to work this out. I have a bunch of colors here with me. Let's see what could possibly work. Let's maybe start with the inside. Why not? Okay, so I'm going to color in the inside red. But what does that mean? It definitely means that none of these guys can be red, right? Why is that? Because all of them are touching this inside circle. Okay? But if none of these are going to be red, I could definitely make this red. So I'm going to color that in red. But if this is red, this can definitely not be red, same as this space. But this one definitely can. So I've kind of used up any space that I can call red. So I'm going to stop using my red. Okay? Let's say I pull out my green. And I want to start filling in this middle piece here. So I'm going to pull out my green for this one. That means that green cannot be used here and here. But I can definitely use it here. Why not? It's not touching the other green space. But then that means I cannot use green in this bigger space because it would be touching this green. And same goes for this. So unfortunately, I'm done with my green. All right, fine. Let's pull out my blue. Let's see what I can do. Okay, I'm gonna fill in a blue here. And same as what I said before, I can fill it in here, but unfortunately it can't fill in these other two spaces because it would touch the blue that I already have. Which means, voila, I need my fourth color, right? I've used red, I've used blue, I've used green. I need a fourth and final color to color in these spaces. And unfortunately, I only have a black marker, so it would be black. So there you go, good guess, 3 or 4 colors, and it looks like I needed exactly 4. No more than 4, definitely not 2 like this star, just because of the way that the spaces are positioned and connected to each other. But there is a perfect example of how this 4-color theorem works and how I decided to choose the colors. Okay, and remember, the catch here is I'm trying to use as least many colors as possible. Okay, so the way that I'm going to challenge you to do this at home, and you'll find it in the package that will be shared with you later today, is just draw any squiggle, have really fun time. Take your pencil, take your marker, and just draw a very funky, I don't know, there you go, and connect it back, a very funky squiggle, and go ahead and start to fill in the spaces. So I don't know, I'm going to choose this random space to be green, and see how you can fill in all the spaces using this idea that no 2 spaces touching can have the same color. So if I just do a little bit of this squiggle, definitely cannot have a green and green here. So maybe I would make this one blue. Right? Maybe I'll fill it in really quickly. This one could possibly be blue as well. Yep. And then I could use my green to go up here because no edge is touching it. Okay, so go ahead and try that out. Have a really fun time. That's probably going to be your most favorite time, just taking your pencil, going crazy over a sheet. But realize that the crazier that your squiggle is, the more spaces you have to fill in. But that could be a wonderful challenge. So go ahead and try that out, and I guarantee you, you will never use more than 4 colors. So go ahead and try that out. And the other challenge I left you with yesterday was, let's take back our star here. And I asked you to start at one point. So let's just start at number 1 here. And see if you can travel all along the lines of this drawing, okay, until you get back to where you started, and you only travel on each line once. Are you able to do it? So go ahead and think about that for a second. Maybe close one eye and trace with your finger over top your screen. Try not to touch the screen. But see if you can do it. This is another idea that arises in math, a really, really cool one. So if you have this in front of you as a sheet of paper, instead of closing your eye and tracing it, you would attempt to use your pencil or your marker and actually trace over top and see if you can do it without lifting up your marker or your pencil and still traveling over every single line. Okay? So while you're trying to guess that, I'm going to tell you that there was once a mathematician, and you might have heard his name. He's a very, very famous mathematician called Euler. And much like we said something about the impossibility when it comes to using more than 4 colors in the 4-color theorem, it is also impossible on certain drawings to trace over every line without lifting your pencil if, and there's this condition, you have a point in your drawing that has an odd number of lines extending from it. So keep thinking about that one. I'll repeat that one more time, and I'm also going to give you another one to consider, which looks something like this, almost like an upside down house. Trace that over again. So can you trace over all these lines only once and get back to where you started? It doesn't matter where you start. You could start here, but if you don't like that, you don't have to. You can start elsewhere. So Euler told us, so if you can try it out or you can use what Euler told us. Euler told us that if you have a point on your drawing that has an odd number of lines extending from it, it's impossible to do this, to take on this challenge and succeed. Let's see, for example, what that means with the star. Every point has 2 lines coming out of it. Is 2 an odd number or an even number? We said it earlier, all multiples of 2 are even numbers. 2 is an even number, which means for this one, it is possible. How could I prove it? Similar to how I drew it yesterday. So I'm going to start at 1. I'm going to go down here to the 4, to the 7, to the 3, to the 6, 2, 5, and 1. There we go. So I managed to trace over all of the blue lines with my black marker only once and get back to where I started. Okay? So for this one, it was true. I could absolutely do that. And again, I could have known that without even trying it out because every point has only 2 lines coming out of it, or an even number. So that one's good. Let's go back to this one. So I'm going to say, I'm going to push this out. I'm going to say here, I could cheat. I could use the work that Euler did for me, his summary of what he found, and kind of use that to determine the answer right away. Because I can see here, even in the corner that I kind of identified as my starting point, that it has 3 lines coming out of it. 3 is an odd number. And Euler said if I have an odd number of lines extending from any point in my drawing, then it's not possible to trace over every line once and get back to where I started. And you can go ahead and try that out. So this one I'm going to say it's nope, not possible. And you can go ahead and try it out and you'll run into an issue every single time you try. So let's say I try to do this with my green marker. So I can try to go down this side. Okay, great. Maybe even go on the triangle, up here, and then what? And then, no, let's try this again. Let's say I do, let's make this bigger actually. Okay, so let's say I start off in that corner. Let's say I even go down and then I go right. Let's say I go up and then I want to take care of the diagonals. This is an example where I run into, where do I go? Do I go right or do I go up? Either way, I'm going to have to trace over a side that I already traced over. So that one doesn't work. I could pull out my blue marker and try it again. Instead of maybe going on another side, I'm going to take a chance in going down my diagonal, let's say. So if I go down my diagonal and then I go, let's say, up from there and then left, just because I haven't tried that out, and down, and then let's say, even if I go on my diagonal, let's say, I'm going to run into the case where all of these lines have already been traced, right? So maybe I should try out the triangle. I'll let you guys try that out, but in this case, Euler told us that it would not be possible. So these are some challenges that you can create on your own at home and pose them to, let's even say, your Mathnasium instructors and see if they can actually tell you if it's possible or not. All right. So before we end off for today, I just want to go back and reflect on some of the symmetry that we've mentioned earlier today, and mention, in case you haven't heard of it yet, reflectional symmetry and rotational symmetry. So we talked about symmetry, a very, very basic symmetry, which you might have seen in the classroom, which we can call reflectional symmetry. So let's say I have, for example, a triangle. Let's say this is an equilateral triangle. I can say that this has symmetry because if I fold it along just the middle here, if I fold it, both sides, all the edges on both sides are going to meet. The two vertices are going to meet. It's going to be exactly the same on both sides, right? And if you need to prove that for yourself, draw yourself a triangle on a sheet of paper, cut it out, fold it, and you'll see that it's exactly right, okay? And if this was a perfect equilateral triangle, if I had drawn it perfectly, you would see that this actually has 3 lines of reflectional symmetry, right? 3 lines of symmetry. I could go and fold it down this way, or I could even go and fold it down this way. Okay? So if you want to create beautiful masterpieces in art, one wonderful element that you can incorporate is symmetry, and in particular reflectional symmetry. It's the most common symmetry that we're used to. But a lot of the figures that we've drawn today and yesterday used rotational symmetry. Now, what is rotational symmetry? Let me pull back the star that we had created earlier. I'm going to let you think about that for a second. I'm going to tell you that this has rotational symmetry. What do you think that means? If reflectional symmetry means that I can fold it and it literally looks like both sides are reflections of each other because they're both the same all along that line of symmetry, what do you think rotational symmetry means? Again, not the most beautiful looking star. Let's pretend it is perfect. But there is rotational symmetry if it was perfectly drawn and perfectly measured. There would be rotational symmetry. Not only that, while you guys are thinking about that, I'm going to tell you that this has, and I'm going to use a specific word here, order. It has an order of 7. And what that means is I can find this rotational symmetry 7 times on this star. It's a 7-pointed star. I also know that it has 7 versions of this rotational symmetry. So if you're guessing what it is, it means that anytime I rotate it, it's going to look the same. Okay? Again, if this was a perfect star, you would see what I'm talking about. Every time I would rotate it with 1 point perfectly up to the top of my board, it would look the same. Right? So it is a star with order 7, meaning if I rotate it the 7 times, same amount each time, it looks the same. It is symmetric. It is rotationally symmetric. Okay? So you can do that with 2D drawings that you create, and we're going to extend it a little bit to 3D objects just for a little bit today. We'll observe more 3D objects in future lessons, but I'm going to pull this to the side and pull up a cube. And I'm going to tell you that the cube, as a 3D figure, also has rotational symmetry. Take a few seconds to think about where, how, why we can say this has rotational symmetry. And I'll just be maybe slowly moving it around. Maybe you can start to see it already. As a 3D figure, and we know that we're surrounded by a world filled with 3D figures, this has rotational symmetry. So let me show you a few areas. And again, we'll look at more 3D objects later down the line. Okay? Let's say I take I'm not going to draw a line through this, but let's say I took a little pole. Let's say I took my marker and I stuck it through the cube in one of the faces. So from the top, I'm designating this to be the top, through to the bottom. Okay? And you're looking at this face here. And I have a pole here, just so you can see it through the camera. If I rotate it 90 degrees, it still looks the same. If I rotate it again 90 degrees, it still looks the same. One more time, it still looks the same, and then I get back to where I started. So a cube, if I have my line of symmetry, I'm going to refer to it as, going straight from the top to the bottom through the cube, it has what we're going to call fourfold rotational symmetry, where I'm rotating it 90 degrees on this face. Okay, that's one example of rotational symmetry in this 3D figure here, the cube. It also has threefold symmetry, rotational symmetry. Now, how can I find that out? Let's say instead of my line of symmetry or this pole of symmetry going through the top to the bottom, it goes through a diagonal. And if you're familiar with that math term, in a 3D figure, it would go from one vertex to the opposite one. So I'm showing you here in the camera. So if I went through this one to this one, okay, and I could rotate it in between my thumb and my finger here. It also has rotational symmetry. Okay? And the way that I like to visualize that is for myself, I just have to rotate it a little bit for you guys in the camera, but you can notice this V here, right? So to get back that V, I turn it once, twice, and then 3 times. So it has the threefold rotational symmetry right there if we're going through the diagonal. And the last one I'll show you before we end off for today is the twofold rotational symmetry of the cube, which is if I rest it on an edge, so we have an edge here, I'm going to rest it on its edge, so you can kind of see it's doing that on my whiteboard. It's a little bit more difficult to see through the camera, but you can see it. So if I rest it there, okay, and then the other edge, the opposite edge, is right at the top, okay, you can start to see that it also has a twofold rotational symmetry here, right? So if I flip it over by 180 degrees, it looks the same. Okay, just a very cool observation. Again, there's so many perfect figures in our world, and from a mathematician's perspective and an artist's perspective, it's nice to look at these perfections in the world around us. And what artists and mathematicians, of course, always try to do is identify them and use them in their work. And so what we'll do in one of our future lessons, and what I want to leave you with to think about today, is how do I take a 3D figure like this and bring it to a 2D world like this? How can I draw some of these cool perspectives that we just looked at today on a sheet of paper? So think about that. That's one of my favorite things to do in the math class. You can create really cool cubes on your sheet of paper that have this perspective. I'm going to leave it there. Thank you all for joining me. I hope that you're loving this connection between math and art as much as I am. I would love to see your pieces of artwork, so if you want to submit them to Nearest Mathnasium so they can share it with us, I welcome you to do that. Have a wonderful day, everybody. Enjoy. If you have rain out there, which I was seeing in the comments, still go enjoy it. And if you have sunshine, even better. Go out and find, maybe out in the nature, some examples of math and art connected with each other out there. Have a great day, everybody. Bye-bye.
It's afternoons that seem to be the most hectic for us, so it was much more convenient when we found Mathnasium at home.
All right, so how do we do half of 5? I think one of the best things about at home is that it really feels like you're almost at home with the student in their house teaching them.
I'm in my comfort zone.
You can just ask for help and the instructor will come right to you.
With Mathnasium at home, I know that they're getting the help that they need.
Awesome, great job.
Mathnasium, changing lives through math.